The first goal of the lecture today is to review the notion of a smooth manifold with boundary. In order to do this, I will present the notion of its topological counterpart, that is the notion of topological manifold with boundary. This is a topological space which is Hausdorff second countable and in which every point has a neighborhood which is homeomorphic either to an open set of Rn or to a relatively open set of Hn, where Hn is the set of points of coordinates x1, x2, xn in Rn such that xn is non-negative. An open set U of Rn, sorry, of M, and a map phi, so U contain them open, and phi which is an homeomorphism onto an open subset of Rn or Hn is a chart for M, where M is the topological manifold with boundary. When it is necessary to make the distinction, we will say that U phi is an interior chart if phi of u is an open set of Rn, and we say that u phi is a boundary chart if phi of u is an open subset which satisfies the following condition: phi of u intersection boundary of Hn non-empty. A point P in M is an interior point if it is okay, let's say if P belongs to U, where U is the domain of an interior chart. P in M is a boundary point if P belongs to U, and this time U is the domain of a boundary chart, and phi of P belongs to the boundary of Hn. Now, how to find a smooth structure on manifolds with boundary. In order to do this, we need to present the definition of smooth map between an arbitrary subset of Rn into Rk. So a map from an arbitrary subset A containing Rn to Rk is smooth if in a neighborhood of each point of A, it admits an extension to a smooth map defined on an open set of Rn. So let's use this definition here in the case of in the case where A is a U open set of Hn. So a map F from U to Rk is smooth if for each x in U there exists U tilde contained in Rn open such that the x belongs to U tilde and F tilde from U tilde with values in Rk smooth such that F tilde restricted to U tilde intersection Hn coincide with F. Now we are ready to say what a smooth structure is. A smooth structure for topological manifold with boundary M is defined to be a maximal smooth atlas that is a collection of charts whose domain cover M and whose transition maps are smooth in the sense that I described before. So M with this structure is a smooth manifold with boundary. In case it's not clear why I need this particular definition of of a smooth map, I would like to say that we need this definition because the transition map are in some cases for a manifold, for a topological manifold with boundary, maps between open set of Hn. Now we are ready to talk about smooth maps. Suppose that M and N are smooth manifolds with or without boundary. A map F between manifolds is smooth if for every P in M there exists coordinate charts U phi for M with P contained in U, Vipsi for N, such that F of P is contained in V, such that F of U is contained in V, and psi composite F composite phi inverse is smooth from phi of U to psi of V. This definition makes sense because these are open set of Hn or Rn. This and this. There is a special case of this definition, which is the one where N is a open set of Rk or Rk plus with the standard smooth structure. This means that the atlas we consider contains just one chart. Domain of the chart is the entire Rk or Rk plus, and the map is just the identity. So in this case, psi will be the identity, and a map F from M to N, in this case, will be smooth if for each point P of M there exists U phi with P in U such that F composed with phi inverse is smooth. An important definition we will use is the one of diffeomorphism. So F from N to N is a diffeomorphism if it is smooth and bijective and F inverse from N to M is also smooth. If F from M to N is a smooth map, and U phi V psi are smooth charts for M and N respectivity, the map f hat psi composed with f composed with phi inverse. This is called coordinate representation of f. Now I will review very quickly the notion of bump function and smooth partition of the unit. So suppose that M is a smooth manifold and let's take a closed subset A and U an open subset which contains A, then a smooth bump function for A supported in U is a smooth function f from M to R satisfying the property that f of x is contained in the closed interval 0, 1 for each x in M, and f restricted to A is identically equal to 1, and support of f is contained or equal to U. If U is an indexed open cover of a smooth manifold M, then a smooth partition of the unity subordinate to U is an indexed family psi alpha of functions psi alpha in infinity m. This symbol denotes the set of smooth functions on M with values in R, satisfying the following properties. Psi alpha of x containing 0, 1 for each alpha in A for each x in M. To support psi alpha is contained or equal to U alpha for each alpha in A. 3. The family support psi alpha with alpha in A is locally finite. So this means that every point of the manifold M is a neighborhood that intersects only finitely many of these supports here. 4. Sum on alpha of psi alpha x is identically equal to 1 for each x in M. I want to mention two propositions. The first one is about the existence of partitions of the unity. So if M is a smooth manifold with or without boundary, and U is an indexed open cover of M, of course, then there exists a smooth partition of the unity subordinate to U. And the second proposition is about the existence of a smooth bump function So once again, M is a smooth manifold with or without boundary. And A contained in M is a closed subset. U contained in M is an open subset such that U contains A. Then there exists a smooth bump function for A supported in U. The next topic we need to review is tangent vectors. So suppose that M is a smooth manifold with or without boundary. Then for every point P in M, I can give the following definition of tangent vector at P. A tangent vector at P is a linear map V. Let's write, no, okay, it's okay. From C infinity M to R, that is a derivation at P that is for any f and g in C infinity M, V of the product f times g is equal to f of P Vg plus g of P Vf. We use the following notation, TPM. This is a set of all tangent vectors at P, and we call it tangent space at P. This new mathematical object is much more than a set. Indeed, if dimension of M is n and phi from U to U hat is a coordinate chart, on the open set U, if the coordinate functions of phi are denoted by x1, x2, xn, then we can define the coordinate vectors d dx1 at P, d dx2 at P, d dx n at P by the following formula. D dxi at P of f, this is d dxi at phi of P of f composed with phi inverse. This definition makes sense because this is a function between open set of the Euclidean space of different dimension, and this is the usual partial derivative with respect to this coordinate. It's possible to prove that d dxi at P provide a basis for TPM, which therefore is a vector space of dimension equal to n, which was the dimension of M. We use also the following notation. Instead of writing d dxi at P, we write just di. So if V is in TPM, V can be written in a unique way as VI, sorry, I omitted something, now it's okay, as the sum on I of VI di at P. Here I am using the Einstein convention, according to which if there are two indices which are repeated, then there is a symbol of sum which is omitted. So this is a sum of V1 dy at P plus V2 d2 at P plus Vn dn at P. If f from m to n is smooth, and m and n of course are smooth manifolds with or without boundary, if P is a point of M, you can define a linear map known as differential of F at P is a linear map defined on TPM with values in Tf of P n by this formula df P Vf. This is equal to V acting on the composite function small f composed with f, where V is in TPM. A few minutes ago I presented the coordinate representation of a smooth map F. Now, what is the coordinate representation of df at P? So if we have that x1, x2, xn are local coordinates for M, and y1, y2, yk are local coordinates for n, then it's possible to prove that df p of vi ddxi at P, so this is nothing but then V written in terms of the basis ddxi at P. This is equal to df at j dxi at P vi dy j at f of P. So here I am using the notation f hat. This is the coordinate representation for f, and I'm using also the Einstein convention 2 times because there are 2 pairs of repeated indices, j and I. So this is a double sum. So we can say that the coordinate representation of the differential dfp is given by the Jacobian matrix of the coordinate representation of F. The next definition that I need is the one of cotangent space. So let's fix P in M, then the cotangent space T star PM this is just the duo of TPM, so we use this notation here. T star PM is TPM star, where this means duo. So this means that T star PM is the space of all real valued linear functionals on TPM. These kind of functionals are called tangent covectors at P. The simplest example of covector is given by the differential of a function in C infinity M. So suppose that you have a function f in C infinity M if you fix P in M, you can define dfP in T star PM by writing dfP of V equal Vf for each V in TPM. The next set of definition concerns some special classes of smooth maps. Precisely, I want to give definition of submersion, immersion local diffeomorphism and smooth embedding. I need the following preliminary definition. Suppose that f from M to N, where M and N are smooth manifold, with or without boundary, has a constant rank if DFP has the same rank at every point P in M. Then F is a submersion if DFP is surjective, that is, sorry, I forgot to write something important at each point P, that is rank equal dimension of N F is an immersion if DFP is injective at each point P, that is rank equal dimension of M. F is a local diffeomorphism if every point P in M has a neighborhood U such that F restricted to U is a diffeomorphism onto an open set of N. that is F is both a submersion and an immersion. And last, the definition of smooth embedding. F is a smooth embedding if it is an injective immersion so not only the differential must be injective but also the map must be injective. That is also a topological embedding. So this means that it must be an homeomorphism onto its image, endowed with the subspace topology. Now we are ready to give definition of immersed submanifolds, embedded submanifolds, and hypersurfaces. So let's write shortly submanifolds. Suppose that M tilde is a smooth manifold with or without boundary. An immersed n-dimensional submanifold of M tilde is a subset M of M tilde endowed with a topology that makes it into a n-dimensional topological manifold. I write shortly top man. And a smooth structure such that the inclusion is a smooth, sorry, a smooth inversion. M is called embedded submanifold if I is a smooth embedding. It's possible to prove that this is equivalent to say that the given topology on M is the subspace topology definitions do not change if we consider manifolds with boundary. I want to define the codimension of M. This is just the difference dimension of M tilde minus dimension of M. If the codimension of M is 1, then we say that M is a hypersurface. And last, an embedded submanifold with or without boundary is properly embedded if the inclusion is a proper map. In the last minutes, I want to review quickly the definition of vector bundle. So suppose that we have a pair of smooth manifolds with or without boundary, and a map pi from E to M, which is surjective, and satisfying the following properties. One, for each p in M, EP by inverse at P is endowed with the structure of a k-dimensional real vector space. Two, for each p in M, there exists a neighborhood U of P and diffeomorphism capital phi from pi inverse of U to U times Rk such that pi restricted to U composed with capital phi is pi where pi U is not the restriction but is the map I'm going to define, where pi U is just the projection on the first factor and for each Q in U, phi restricts to a linear isomorphism from EQ to Q times Rk, which can be identified with Rk. A bit of terminology. M is what we call the base of the bundle. E is what we call total space. Pi is what we call projection. EP is what we call fiber of E over P. And the diffeomorphism phi described before is what we call smooth local trivialization. The tangent bundle we will use very frequently in this course is the following. E is equal to Tm, defined as the disjoint union of the tangent spaces to the manifold. And let's say that we finish lecture just giving a few more definitions. Sorry, I forgot to write the name of this bundle. This is what we call tangent bundle. And I want only to say that if pi from E to M is a vector bundle, then a section of E is a continuous. Let's write also here smooth vector bundle, continuous map, sigma from M to E, such that pi composed with sigma is the identity of M. So this formula says that the section sigma is a right inverse of pi. Equivalently, you can say that sigma p belongs to the fiber EP for each p. If U contain or equal to M is open, then a local section of E over U is a continuous map sigma from U to E such that pi composed with sigma is the identity of U. And last, a smooth local or global section of E is a section which is smooth as a map between smooth manifolds. If we drop the hypothesis that the section is a continuous map, instead of having the word smooth in the definition, we will have the word rough. So a rough local section is a map sigma from U to E, which is not necessarily smooth or even continuous, such that pi composed with sigma is identity on U. I think is a good point where to stop. Thank you for your attention.